talk is given by Abdul Sami Al-Fawzi.
Good afternoon, ladies and gentlemen. So I will talk today about the spectrum of the ethylene in the 10 micrometer using D2H2 data system. So I would like to start by introduction and general ideas about the molecule of ethylene, and then I will talk about the experimental conditions, and after that I will just briefly explain about the theoretical model that we have used in this work, and after that I will show you the results and analysis, and to finish up this presentation I will talk about the conclusion and our perspective for the spectroscopy of ethylene. So let's start with some interesting about this molecule and why the ethylene. Actually, ethylene is a naturally occurring compound in ambient air that affect atmospheric chemistry and global climate, and it's also affect at the concentration of ozone layer, which absorb more than 97 of ultraviolet radiation. In the Earth, ethylene can be considered as a pollution which produced by many factors, and for example by biomass fire and plant life, and can be rejected from many applications in industrial chemistry. In the atmosphere, the photochemical reaction with some molecule can produce also some molecule that has influence and affecting this atmosphere. Ethylene also, it was detected in the atmosphere of outer solar system bodies such as Jupiter, Saturn, Newton, Triton, and more recently, ethylene was supposed to be present in the atmosphere of exoplanets such as GJ 4360. From another hand, ethylene can be considered as a most important organic chemic in industrial chemic, which can be considered as a building block of many vast lab applications in industrial chemic, which start from fabrication all the type of polymer and plastic. So everything that's around us is fabricated from ethylene, and that's explains the increasing production of this molecule. More than 156 million tons of ethylene was produced in 2013. So there is a really need to investigate its infrared absorption over a wide range spectrum. Ethylene is a molecule of D2H symmetry, which having 6 atoms. So it has 12 fundamental vibrational modes, of which 5 are infrared active, and 6 are Raman active, and 1 being infrared and Raman inactive, which corresponded to nu4. But actually, its transition can appear in the experimental spectrum only because of the transfer intensity from nu7 to nu4, which caused by Coriolis interaction, as we can see from this figure. This work is devoted to study the high resolution of spectrum of ethylene in the range of 10 micrometer, which including 4 fundamental vibrational modes, of which nu4, nu7, nu10, nu12. And this range spectral is very important because the optical remote sensing of ethylene in the planetary atmosphere is relying on this range spectral because of the strong absorption of nu7. So this work is relying on theoretical spectroscopic information available in literature and retrieved from high resolution spectrum, which were recorded by our collaborator in the University of Brussels by Mr. Jean van der Auwera. And a total of 8 spectrum were recorded at a resolution of 2 times 10 minus 3 wave number, and at room temperature stabilized by an air conditioning system. And after the calibration, the accuracy of this spectrum was estimated to be better than 10 minus 4 wave number. This table shows all the physical condition of this spectrum, such as the pressure and path length absorption and the temperature. So, as it's mentioned in the title of this presentation, this work was carried out using the theoretical model that we can call it Day-to-Arch top data system, which is one program of XTDS software, which was created by our collaborator in the University of Dijon, and which consists of a series of programs written in Fortran, and which relies on growth theory, tensor formalism, and vibrational extrapolation method. This model has many advantages, such as it allows the treatment of many complex problems of the spectroscopy, and it provides all the symmetry level for the state and for the operator at the same time. And as we mentioned, using the vibrational extrapolation method allow to get parameter in which always the parameter of an excited state contain information from the lower state. In another word, and just an example, let's imagine that we want to feed the rotational constant of the ground state K0 and its variation in the excited state delta B, C. So here we don't feed them separately, but we feed them together. And this allows, as we mentioned, to get parameter in which we have the information for the excited state and for the lower state at the same time, and this what we can call it the global analysis or simultaneous feed. So let's imagine that we have one molecule where the vibrational energy of this molecule are grouped in a series of clusters, which we can call it collides, as designed here, P0 till Pn. So at first we apply some transformation of contact to each level of this collide to remove the interaction between them, and then the Hamiltonian of this molecule can be described by the sum of these collide as it's shown in this equation. And each level of this collide can describe as a linear combination of Riemann proportional operator, as we can see from this equation. Here in the first term we have the parameter of model to iterate from the wave number of experimental spectrum, and here we have in the next part the proportional operator. And so we can describe also the effective dipole moment in the same way, but this time by taking consideration the dipole moment which we can retrieve from the intensity of the experimental spectrum. And applying the vibrational extrapolation method allow to create all the collide that have taken in consideration, which start from the ground state till the collide, last collide. So to start this work, the most of this, the initial value of this parameter were taken from our previous work, which is about frequency and intensity analysis of mu12, which was carried out by Roger et al. And other parameters also were taken from previous work about ethylene, such as Wheeler and Rusinek. And as the parameters in this work were given and reduced Hamiltonian, so at first we translate them to be adapted with our formalism by using some equation that reported by Vincent Bourdon et al. So this parameter allowed to calculate an initial spectrum which were compared and assigned with the observed spectrum by by using the STView program, which is one program related with XTDS, which allow the assignment between the observed and the calculated spectrum. Here we have the blue spectrum is the calculated spectrum, and in the upper panel we have the prediction of its transition. And the red spectrum is the observed spectrum, and also on the upper panel we have the peak list of this spectrum. So as we can see at first, a limited number of observed lines were assigned with calculated spectrum, and then we have fitted this assigned line by using the model that we have explained about to improve the parameter of Hamiltonian, which in turn were used to calculate a new spectrum, as you can see here, which including a new transition and a new line. So again, we have assigned this new line and transition, and then we have fitted them again, and then so we have repeated this procedure many times till no more line observed can be assigned in the calculated spectrum. Another problem that we have faced during this work, as you can see in this range, we have a close agreement between the observed and the calculated spectrum, and then one can see that the calculated transition are shifted with respect of the observed spectrum. So we have assigned this line and then fitted them, and after that, as you can see here, we got a good agreement between the observed and the calculated spectrum. So the procedure of assignment and intensity, it was in the same way, and these two tables show the statistic of line assigned in position and intensity. Here we have the number of data assigned for each fundamental vibrational mode studied in this work, and here we have GMX and KR, and here we have the standard deviation. And here in this table we have the same things for intensity. Actually, we have assigned only 1,645 line intensities because we fixed the threshold between the observed and the calculated only to 10%. And this figure shows the results, the residual results from the field on position. As you can see, no systematic deviation can appear in this figure, which improves that all the parameter and line were included in this fit. And here we have the same things for assignment and intensity. And here we have a comparison between the observed and the calculated spectrum. Here we have mu 10 and mu 7 and mu 12. And here we have comparison between some translation or between the observed and the calculated. As we can see, we have a good agreement between the observed and the calculated spectrum. Here we have the comparison between the observed and the calculated of mu 7, which including some transition of mu 10 and mu 4. And here we have the residual results from this field. And here we have the same comparison, but with another pressure. Here we can see clearly the some transition of mu 10 and mu 4. So after finishing the assignment and the comparison between the observed and the calculated spectrum, we completed this work by comparison with the data available in Hytron. And here we have the comparison of mu 10. Here we have the residual results from this work, and in green one we have the residual results from the comparison with the data available in Hytron, which corresponded to the version 2000, which was carried out by Kuwait et al. And here we have a comparison between the results of this work and the data available in Hytron for mu 10. As you can see here, there are a lot of line positions that are missing from data available in Hytron. And here we have the comparison between the observed and calculated spectrum of mu7, which also corresponded to the version 2000 of Hytron, which was carried out by Kuret et al. Here we can see that there is a good agreement between these two results. And here we have the comparison for mu 12. Here we have the residual results from this work, and in green one we have the comparison for Hytron, which corresponded to the data of 2008, which was carried out by Roger et al. Here we have a comparison between the calculated and results from this work and the data available in Hytron. As we said here, we don't have we didn't compare the experimental with the data available in Hytron because, as we mentioned, it's this new form is forbidden, and it can be detected from correlates interaction between mu7 and mu4. So here we have comparison between the data available in Hytron and the results of this work for mu4. So we have performed a global analysis in intensity and in position of mu4, mu7, mu10, mu12 of ethylene at 10 micrometer. We have assigned 10,757 line position with an RMS 2.6 times -4 wave number, and to get these results we have treated only 70 parameters of Hamiltonian. So after that we have assigned the experimental spectrum in intensity, and we have assigned 1,645 line intensity with an RMS 2.5%, and for that we have treated only 17 parameters of dipole moment. This work actually can be considered as the first work which dealt with the intensity analysis of this tetrad in this region. And as we have seen, it's provide an improvement over the data available in Hytron, and especially for mu10. So what's the next? We have already recorded the same spectrum for the same range, but for the isotope of 13C2H4, and now we have finished the assignment and analyzing in position. So we will complete by assignment in intensity. So there will be cooperation between these two isotopes, and also this work will be followed up by another work that we have started but not finished yet, which corresponded to analyzing in frequency and intensity of mu9 and mu11, which located at 3 micrometer. So to get more information, please see our journal that have published recently. And finally, I want to thank all the people that participated in this work, and I want to thank you for your attention.
Actually, I had two questions. Can you show again the comparison between your calculations, like empirical calculations, and with Hytron for new 10 band?
10?
New 10, yeah.
Okay.
Right, yes,
Should we
so,
have this one and then this one?
yeah, this one. So, like, it seems that you have more stuff right on the left calculated bands, but now show, if you show earlier on comparison of the experiment with your calculation, if you go up for like a few slides, there's a comparison of your calculation with experiment in new 10 bands. Yeah, here. So experiment often looks like Hytron. To me, it kind of like cuts off at some point, like on the very left hand side.
Actually, here I have taken one spectrum because I had, as I mentioned, in the experimental conditions, we have here we have many spectrum for a new 10.
Right.
So what I have taken, I have taken one spectrum to compare. Actually, this range, it was recorded in the same spectrum. So here I didn't didn't put it because I can't put all that figure. Here we have the same spectrum here in the same range. So
So you basically artificially cut off
yeah,
the
actually we
spectrum.
have
Okay,
another spectrum,
Yeah.
observed spectrum that starts from here. For sure.
Okay, good, good.
Yuri,
So I actually had sorry, sorry, go ahead.
Yuri, if I may, as Sami showed, we record 3 spectra with a path length of 7 meters or almost 7 meters, and these go lower in energy, specifically for the Newton band. And in fact, we see only the B branch because the R branch is buried in the
Okay, I understand now.
So, but as he showed, only one of the spectra recorded with a short cell, 20 centimeter. These were stopped at about 700 centimeters.
Okay.
So that's why you have this cutoff, which happened to fall exactly where.
Where hacker was, that's why I was confused. Yeah. So I actually had another question. So you know, just from a side readers, there are so many papers now from your group, from Olenikov's group, and from Lafferty Flow groups. And I guess my question: do you, in your feed, global feed, do you include their data as well, or you include only data from your experiment?
From data from Olenkov?
For example.
No, actually, in this work we didn't take anything from Olenkov. This actually all the data were taken from experimental spectrum except of 213 line intensity, line position. 200 were taken from Rozinet, and 13 were 13 line were taken from Legrand.
Okay, I'll rephrase my question. Do you think if you would have taken some line positions from Olenikov, would it improve the predictability range and the accuracy of your feed?
Actually, I saw the journal of Olenkov, and I didn't, for example, I didn't saw any comparison between the observed and the calculated in that journal of Olenkov. So I didn't do compare with Olenkov. But as I said, because in journal of Olenkov, there is no comparison between the observed and the calculated. We can see only the observed spectrum, and but there is no comparison between the calculated and the observed.
But there is actual data there. I'm pretty sure he did, like at least in some of the papers, I did see line positions reported.
Yeah, for sure. Yeah, actually, Olenkov did the assignment on position, and this on position and intensity.
Right.
Actually, this
John has a comment.
So if I may again, sorry, we did a comparison between using the data of Olenikov, the observed positions, and the calculated positions generated using the XADS model. And what we get is a standard deviation which is twice as large as the standard deviation reported by Olenikov. And for almost, they published 13,000 observed line positions about, and we matched about 11,000.
Okay.
So it's about the fact